Hello and welcome to ESC Live. We are live today from the Coast Laboratory. This is the Coastal Ocean and Sediment Transport Laboratory at the University of Plymouth, and we're going to find out all about renewable energy generation out at sea and some fantastic research. You're going to meet some brilliant engineers and they're going to tell you all about their career paths and what they do here, and so we're really looking forward to that. Hello to Egg Buckland School and to ACE Tiverton. Really nice of you to join us, and we hope you enjoy today. You've got a worksheet to go through, and you can ask questions live as you go along, so make sure you do that and we'll try and get through as many as we can. So I'm Dr Alice Mills. I'm one of the directors of Exeter Science Centre alongside Dr Natalie Whitehead, and we're joined in our presenting team today by Professor Adam Feldman from the University of Exeter. So initially I'm going to hand over to Adam just to talk to you about why research like this is so important and just to give us a bit more context for it. Hi Adam.
Thank you, Alice. I'll just get the microphone in place. So, hi everyone. My name is Adam Feldman, and I'm a Professor of the Understanding and Learning of Renewable Energy at the University of Exeter. But I'm actually positioned not in Exeter, but in Cornwall, near to Falmouth. Now, we're at the Coast Lab today, specifically to learn about offshore or marine renewable energy. So before we go any further, it's very important that we understand what energy is and what renewable energy is. So energy is a scientific term that we use to describe the ability to do work. Everything that moves or produces some activity, that can be why does a car move or an aeroplane fly or your computer work or a light bulb produce light, it requires energy. And over the past couple of hundred years, humans have tended to power all these machines and inventions, as you know, from fossil fuels like coal, oil, natural gas. And there's a problem with burning these fossil fuels in that we produce a lot of greenhouse gas, in particularly carbon dioxide, and we're damaging the environment. But we don't have to burn the fossil fuels because all around us is a replenishable source of renewable energy. So renewable energy, if we were to define it, is a replenishable form of energy that reforms itself within a human timescale. And there are, in fact, 7 varieties out there, like sunshine, wind, and so on. But we're here today specifically to look at the types of renewable energy that we can get from the marine environment, the sea environment. And there are 3 main types. We can capture wave energy, the energy in the waves. We can capture the energy in the flow of the tides, tidal stream energy. And we can also very efficiently capture marine wind energy with much larger wind turbines placed out at sea as opposed to on the land where there's more space and the winds tend to be more constant and we can be more efficient in our capturing of offshore wind. So I'd like to hand over to Natalie and Deborah, who are going to take us further in the story of offshore energy and how we investigate it.
Thank you very much, Adam. So hi, everyone. I'm delighted to be joined here today by Professor Deborah Greaves, who is the Director of the Coast Laboratory and Professor in Ocean Energy. Deborah, thank you so much for welcoming us here and letting us come to this amazing facility. We can see that the waves are going now. Could you maybe show us around and tell us a little bit more about this exciting facility?
Certainly. Thank you, Natalie, and hello to everybody. So my name's Deborah Greaves. As Natalie says, I'm Professor of Ocean Engineering here at the University of Plymouth and also the Director for the Coast Laboratory. And I'd like to welcome you and introduce you to our fantastic Coast Laboratory here at the University of Plymouth. And following on from what Adam was saying, what we do here is we like to scale down the conditions that would be experienced at sea into a laboratory controlled environment so that we can run experiments and learn how these new structures and these offshore renewable energy types actually work. And I'd like to tell you something about how we do that here. We do a lot of research in offshore renewable energy, and at the moment we're leading something called the Supergen Offshore Renewable Energy Hub. There's lots of resources and information there that you might like to look into. But within offshore renewable energy, we include offshore wind, wave energy and tidal stream energy, as Adam has said. If we look over here, we can see we've got a very large ocean basin. This is this large basin. This is our ocean basin. It's a little bit like a swimming pool in terms of its scale. It's actually 35 metres long, 15.5 metres wide, and at its maximum operating depth, it's 3 metres deep. What you can see at the moment is a number of small waves being generated, and those are generated using these flap-type wave paddles here. We've got 24 air piston controlled wave paddles. They've got a 2 metre hinge depth. That means we can generate waves in the wave tank of up to just under a metre wave height. So that's pretty dramatic when we have the big waves going, believe me. There's a beach at the far end, so the waves crash onto the beach at the far end. The idea is that not too much of that energy is reflected back, but what is can be absorbed with these active wave paddles. But not just the wave generation, we also have within this basin a current generation system that goes along the tank and another one that goes across the tank. And that means that we can recreate the conditions at the sea, including the waves and the currents. And very soon we're going to be installing a wind generation system as well, so we'll be able to have wind, wave and currents all combined together.
Fantastic. I wonder if we can have a little walk around to see what you've got in this amazing lab, because it's nice to take in this incredible view. And this is a real working laboratory, so you'd have academics and students working here and testing out devices?
Yes, absolutely. So we have our students, we have some talk programs here. We teach coastal engineering and offshore renewable energy, various things. So the students run experiments. We also do a lot of research, funded research and with external partners. And also we do a lot of commercial work. So we have people developing these new technologies want to come and test them and use this facility to test out their ideas. We're going to have a look in more detail at this experiment when we go downstairs, but this is an example of a floating offshore wind turbine. And then here we have this is our coastal basin. So this one looks a little bit different. It's a shallow water basin. So whereas the other one's the ocean basin, and I mentioned that the wave generation paddles there are hinged flaps, that means it's just activating the top section of the water column to generate an offshore or a deep water wave. Here we generate shallow water waves. So again, we've got a bank of wave generators here, but these are piston type wave generators. And if we get to see them in action, you'll notice that they move backwards and forwards with a vertical front face. So that's activating the whole of the water column, and that's generating a shallow water waveform.
Perhaps I think we're going to move around there, and then Adam is going to be having a little look in more detail at that fantastic floating offshore wind demonstration.
Here are Anna and Emma. Welcome.
Hi, thank you.
So, first of all, let's find out what these two engineers are researching. So Anna's working for a PhD in marine energy engineering. So, Anna, tell us a little bit about your research. What are you studying?
So my research is about cables for wind turbines. So a wind turbine like this that's floating needs the electricity to be taken onto the shore so that we can use it in our homes and everything. And so the cables have to go from the wind turbine to the seabed, and they have to be able to withstand all kinds of loads from the turbine moving around and from the waves themselves. And so I'm designing those cables to work better and to make sure that they don't break, essentially, in the 25 years that they need to be there.
So these electrical cables are continuously moving, is that right? And if we bend them about too much, they'd snap.
Exactly. We literally call them dynamic cables, and so they're built to be really flexible, but they also need to be able to not break.
So as you probably have seen offshore wind turbines, the majority of them are planted in the sea, but the turbines we're now researching are floating in the sea. How big are these turbines these days, Anna?
Well, we're looking at 15 megawatt offshore floating wind turbines, so that's pretty big. And the challenge is that the further you go offshore, the more wind there is, but then it's in deeper waters, and so they have to be floating, which obviously has its own challenges.
So these are really big machines. I think, am I right to say they would be 230, 240 metre blade diameters? Just imagine standing at the end of that 100-metre running track on your sports field. Think how long that is, and more than double it, and that is the size of the blades across on one of these. And the 15 megawatts, I think you're saying about, can power 15,000 homes or 60,000 people's electricity.
Yeah, it's
Wow, this is
it's
big.
big scale, yeah.
This is big engineering. So Emma, Dr. Emma Edwards, she studied and obtained her PhD in marine energy, I think.
Ocean
in the States.
engineering.
Ocean engineering.
Yeah, that's
Tell
right.
us about your research to get your PhD and now the research you're doing here.
Yeah, so my research during my PhD was on wave energy, so converting energy from ocean waves into electricity. And what I looked at during my PhD was optimizing the shape of the wave energy converter, so how we can get more power out from changing the shape of the wave energy converter. And what I work on here at the University of Plymouth is floating offshore wind, and particularly I'm looking at this model scale floating offshore wind turbine that you see in the tank. So this is 70th scale of the 15 megawatt turbine. And I'm looking at how to model it in the lab. So instead of using a turbine on the top of the tower, we have these drone propellers. It's a real-time controlled drone propellers that simulate the aerodynamic force. So instead of having the turbine on the top of the tower, we've replaced it with these propellers that we can control in real time. And the little dots that you see on the tower there, we track the motion of those little dots. So as the turbine is moving back and forth, it's actually in real time changing the force that the turbine will have on the tower. So we control in real time the propellers. So yeah, that's how we physically model the floating offshore wind turbines in the lab. That's most of my research here.
Emma, that's brilliant. Anna, where would your cables that you're researching be relative to this model out here?
Yeah, so I've actually got to run some experiments on that. So the cable fixes just under the platform, and then it goes down to the seabed. And you typically have it's called a lazy wave shape. So it comes down from the turbine, and then it has a bit of a floating section, and then it connects to the seabed.
So what depth of water would there be underneath the real wind turbine?
Well, this is simulating a 200-metre water depth.
Wow.
Yeah. So luckily we don't have to work in that kind of environment, and that's what this is for.
So folks, what we are looking at here is a model. The real turbine, that tower would be about 150 metres tall, and the turbine blades would be going up another 120, 130 metres above that. Have we got any questions, by the way?
Is it possible to connect solar panels to a wind turbine's blades?
The blades are moving very, very quickly. So the solar power, putting solar power on the blades won't really work because it's moving far too quickly. But there could be solar powers maybe along like the platform, like on top of the platform. So I've seen, combined floating offshore wind and solar platforms incorporating the solar panels to the actual platform instead of the blades.
We've got another couple of questions. So Sally has asked, how much did the wave tank cost to build, and how long did it take to build?
Well, that's a good question. It's a bit difficult to say how much it cost to build because it was actually built as part of this whole building. Right. So obviously this is we're on the ground floor and it's built into the basement of the building. So the total cost of the building was about 18 million, I think, something like that. And it was opened in 2012. So it's been running for 10 years, and we're having our 10-year anniversary this year. But yeah, I think the wave tanks themselves, probably 1 or 2 million of that, but it's a bit difficult to say.
Right, so an expensive project. Anyway.
Yeah, it's not something that you can buy every day.
No, probably not one for your schools, but that means you can come and visit here. And there's another question from Miss Jeffrey's class. The pool is really small compared with the sea. Can it take tides into account?
Oh, well, that's a really good question. We can take tides into account in that we can operate at different water depths, so we could operate at different stages in the tide. And there's something really clever about this wave basin in how we do that, because we don't drain the water down when we want to run at a different water depth. We move the floor. So the floor, which you can probably just about see through the water, that's got a mechanism that raises it up out of the water. So the water stays where it is. Floor comes right up out of the water. We can fix our model to it and the mooring system and the anchor, and then we lower the floor back down through the water and stop it at whatever water depth we want to run. So we can't simulate the progression of the tide coming in and out here, but we can run it at different water depths, and we can also do experiments to simulate the tidal streams and the tidal currents that occur as the tide comes in and out.
Fantastic. And one last question from Miss Jeffrey's class. Do you do work experience placements for year 9s going into year 10s, or are they still a little bit young?
Yes, we do, or we have done in the past. We've had a little bit of a break, like most people have during lockdown, but I'm sure that's going to open up again very soon. So if people are interested, they should go to the University of Plymouth website, and there'll be a way to apply through there.
Fantastic. Thank you so much. Brilliant questions, everyone. Really, really impressed. And it was really great to hear from Emma and Anna there about their research and the awesome work they were looking at in terms of these floating offshore winds. Now, I wonder, Deborah, can you tell us a little bit about the different ways that we can generate electricity using wave energy and things, as we're showing here?
So there are many different types of wave energy converter. And as I think Adam mentioned, what we're using is the kinetic energy in the waves. And I think someone had a question around the red floaty things in one of the pre-event slides. And this is an example of one of those red floaty things at a very small scale. This is our mini tank, which we use for demonstration of the concepts of wave energy. So you can see this one is a raft with some hinges and lots of different sections connected together. And as the wave is generated by my assistant here, then you can see the different sections are moving relative to one another. And in the hinge, if we put a power takeoff, type of power takeoff, which will convert that motion into electricity, then we can generate electricity. So this is called a floating hinged raft, or articulated floating body.
I suppose the important thing with these is they're usually taking the motion of the waves directly and using that through electromagnetic induction to move, have relative motion between a coil, a conducting coil, and a magnetic field to generate electricity.
There's another demonstration of that here. So this one, we've got different sections floating on the surface. And then over here you can see this is called a point absorber. And if we can get the waves to generate at just the right frequency, then the yellow part is a buoy, and you can actually see the copper coil there, and inside this column we have some magnets that you can see there. So what we've got, if we get exactly the right frequency, and this isn't playing the game for us today very well, but we should be able to see this bobbing up and down in the waves, and you can see the coil is moving through the magnetic field, and that's generating the electrical induction. Oh, we've got another demonstration of that over here. Yeah.
Adam has a nice demonstration of this here that he's made himself.
This was a little toy knocked up yesterday in our lab.
He's such an engineer.
And what we have are some magnets here and a coil of wire. And this is called a linear generator. And as the magnetic field passes the coil of wire, you've probably learnt about electromagnetic induction. We get electricity produced in that coil of wire, and we can see that the light-emitting diodes give us a flash as the magnets pass through the coil. Now, this is actually a little point-absorbing wave machine, because like the one we have in the tank, this toilet cistern float that we've got at the bottom, if it was sitting on the waves as a point absorber of wave energy, would oscillate up and down, and it's a simple wave energy conversion machine.
And it doesn't depend on which way the waves are travelling, which is really nice. I was just going to very quickly, because I think we've really got to move on to the next part. But what I would just show is perhaps this lovely this demonstration here.
Okay, thank you. So at this end, we have something called an oscillating water column. This one is fixed, and what's happening is as the waves go up and down, there's some air trapped inside this chamber, this glass chamber. And as the waves go up and down, it changes the volume that's available for that air. And so some of it's going to be pushed out through this duct and then drawn back in again as the wave level goes down. And you can see what's happening in this duct. We've got a turbine there. It's a unidirectional turbine, and it's spinning. And as it's spinning, we've got a generator in there, just like we would in a wind turbine, and that's lighting up the diodes. But what you might notice, if you look very carefully, is that this turbine is stopping and changing its direction. And that's because it's a unidirectional turbine. It only operates in one direction. So when the air is coming out of the duct, it spins in one direction, and as the air is drawn back through the duct, it spins in the other direction. So that's quite good, but we don't really want something that's going to change direction all the time, because that's going to wear the bearings and the structure. So in this duct, we have a different type of turbine. And if you look very carefully there, you should be able to see that it's not stopping and starting, it's not changing direction, it's spinning in the same direction, no matter which direction the air is going. So we've still got the air going out and in, just like we did in that one, but the turbine this time is spinning in the same direction.
So you could potentially build these into sea walls and use the waves.
So these can be built into sea walls, like this example here. In fact, there is one in northern Spain that's been operating for about 10 years now, I think, generating electricity to the grid. But they can also be built into offshore floating devices as well. So we've also done quite a lot of experiments with floating oscillating water columns as well.
So exciting, and there's so much engineering in here. So hopefully we're inspiring a few of you with lots of potential engineering solutions. We're going to move on to your engineering challenge now. Thank you so much, Deborah. And I'll pass this on to Alice, who'll give you a bit of an introduction to that.
Firstly, thank you so much for all the brilliant questions coming in. We will get to those, and we've got a Q&A after this little break, so we'll make sure we cover lots of those questions. And anything that isn't answered, we'll send through a spreadsheet of answers to you all later. So thank you for interacting. It's great. So a little challenge now. You've got 5 minutes. We want you to try and answer this question. The government wants to increase the capacity of offshore wind generation from the current 10 gigawatts to 50 gigawatts by 2030. Estimate how many wind turbines would need to be installed by 2030 to supply this capacity. So on your worksheets, you've got a little bit of info to help, and we want to hear your different answers, so put them in the chat when you've come up with something. So, yeah, and there's a bonus question if you get through that. By 2030, how much carbon dioxide will be saved each year compared to generating electricity by burning gas in a gas power station? So try and work that one out. That's a bit trickier, but have a go. So send us your answers in the chat, and we'll see you in a few minutes.
So, Alice, have we got some answers for the problems?
We have. So, Mr. Lyon's class has said we've got estimates between 312 and 3 million more turbines.
For the number of turbines?
Yes. So quite a range there, I'd say. It was a tricky one, and then someone else has said wind turbine estimate 5 times more than currently. So, yeah.
Yes, that's not a bad answer, that second one. Let's have a think of what the answers we'd come up with for these questions. First of all, the simple answer is we need about 4,000 new large offshore wind turbines. And we'll come back to that one in a moment. And the number of tonnes of carbon dioxide emission that we'll save from going into the atmosphere if we get to 50 gigawatts of offshore wind will be 40 million tonnes of carbon dioxide. But let's just concentrate on that first question. And it becomes quite an easy problem to solve if we understand and use what's called engineering or scientific notation. It's an understanding of how we talk about kilo, mega, and giga, because engineers tend to use these prefixes to numbers as numbers get 1,000 bigger. Let's just spend 30 seconds thinking about what energy is. As you know, you measure energy in the unit of joules. So that you can put a size on what 1 joule is, I've brought along a really important prop. It's an apple. An apple has a weight of about 100 grams, so it's a force of 100 grams or 1 newton. And if it falls 1 metre, 1 newton through 1 metre, force times distance, shows us what 1 joule is. We'll often talk about kilojoules. That would be 1,000 apples falling 1 metre. A megajoule would be 1 million apples falling 1 metre. And 1 gigajoule would be 1 billion apples falling a metre. Now, the power of these turbines and the power of electricity that we require is the number of those joules per second. So what a 10 megawatt turbine, like a big offshore turbine, is producing is 10 million apples falling in 1 second, equivalent of electricity. And what we want is, in fact, 40 billion extra apples falling a metre a second. And we divide the 40 billion by the 10 million from each turbine, and that tells us that we want 4,000 extra turbines. So 4,000 is an approximately good answer, which is 5 times, roughly, of what we've built already, even though turbines have now got bigger. But at this stage, I'd like to pass back again to colleagues for discussion of engineering careers. So well done, everybody, for working. We've got some very decent answers there.
Fantastic. And did you go into the kilograms of CO2? I don't know if you mentioned that.
Yes.
Yes.
We talked about saving about 40 million tonnes of
Fantastic.
CO2. And we can go, your teachers have the workings for that, and you can go through it on the blackboard afterwards. But I want you to consider being crushed by that weight of CO2 each year.
That's a nice visualisation.
CO2.
Fantastic. We've got lots of questions from you. Thanks so much for contributing them. Alice is going to be asking them to we're going to swap microphones.
Okay, thank you so much for sending through your questions. So, oh dear, it's a hot day today, and someone's asked, can you swim in there?
Not advisable, no.
And that was Ben. And then Josh has asked, how much does it cost to run, and is it powered by 100% renewable energy?
Well, that would be nice, wouldn't it? I don't think I can answer either. Well, I can answer the second question. How much it costs to run is difficult. But it does run, it's very popular, and it does run pretty much every day. So we have a lot of experiments going in here. Is it powered by renewable energy? No, I wish it was. But we're building a new building next door, which is going to have lots of solar panels on it. So that's good news.
And then, sorry, I've got the mic there, haven't I? Ace Tiverton has said, do you model for freak waves? So when, I guess they're thinking about the floating wind there. Do you model for freak waves?
Yes, we do. So that's actually a big aspect of what we do in the Ocean Basin is actually look at extreme responses. So how the platforms move for extreme sea states. So a sea state that you might see once every 50 years. So to make sure that the platform doesn't topple over or float away. So that's a really important part of what we do.
Brilliant. And Dylan has asked, how big can the waves get in the wave tank?
So that, well, with regular waves, the maximum waveform we can generate is a metre wave height. So that's the distance from the trough to the crest. That's pretty high, and it makes a big booming sound when it crashes on the beach. But the thing we can do to generate those focused waves, those freak waves or extreme waves, is to focus together a number of waves, so we can generate a really big wave in the tank. But again, that's around about a metre wave height.
Brilliant. Mrs. White's class has asked, does the tank water temperature and the salinity match seawater?
So yeah, that's a really good question. And when you're scaling these devices, you need to take that into account, because seawater will mean that the device will have a different submerged weight when it's being modelled. And so that is something that we have to take into account, because this is fresh water.
Brilliant. Fantastic. I've had so many good questions. Poppy has asked, how do these things, the turbines, etc., affect ecosystems?
It's funny that none of us want to answer that. It's a great question, and I think engineers are working more and more with ecologists and biologists to work out what effects it will have on marine life. But it is a really important question, especially in terms of making all of these technologies accepted by the public.
Definitely. Brilliant. And then we've got some careers questions here. So Caitlin has asked, what sort of pay do engineers make? It's always an awkward one. You don't have to be specific, but a general answer would be lovely.
Well, I think it's reasonably well paid. I think starting salaries for graduate engineers probably in the mid-20s, something like that.
Brilliant. That's not bad at all. And Sally has asked, how many hours of training does it take to be an engineer? You can give it in years if you prefer.
But in order to become an engineer, to become a chartered engineer, first of all, you need to have a degree, an undergraduate degree. And if you want to be a fully chartered engineer, you also need that to be an M-level degree. So you need either to do an integrated master's or to do a bachelor's degree and then an MSc, a master's degree. And then after that, you need to go through a period of professional training and assessment. And then you can join one of the professional bodies. So if you want to become a civil engineer, you can join the Institution of Civil Engineers. If you want to become a mechanical engineer, you can join the Institution of Mechanical Engineers. But normally it takes probably about 4 years after you've graduated with your master's of professional training and then towards the examination with the professional body.
How often do you have to change the water? Asks Josh.
Okay, sorry, another for me. So actually, with our very clever floor, which moves up through the water rather than draining the water down, we don't need to change the water very often. We only change it for maintenance purposes, so ideally, probably every couple of years.
So living in the southwest of the UK, you probably realise that our country, the United Kingdom, is completely surrounded by water. We're actually very lucky as far as marine renewable energy resources are concerned in the UK, because we're right at the edge of the Atlantic Ocean, and we have a huge wind resource blowing onto our country, a great wave resource, and some of the best tidal resources anywhere in the whole world. But in order that we can capitalise on that, we need facilities like we've been looking at here today, so that we can design, build, make more reliable and run the amazing engineering devices. Probably one of the take-home things from today is how big some of these machines are. They're absolutely monumental in size. I want you just as a final thought, to think back to that 100-metre running track that's probably out on your school sports field. And now imagine turbines floating in the sea with blades 2.5 times the diameter of that 100-metre running track. A huge mass that the engineers here are working out how to keep stable, running in the ocean, and bringing that electric power back to us and our homes. So thank you. And in the very final thought, over to Nat again.
So thank you so much for joining us, everyone. Hope that's been really inspiring. Think about all the exciting opportunities for engineering in this area of engineering and in so many others. Thank you for joining us. Teachers, students, please fill in the feedback forms next. That's your next task. But thank you very much for joining us. Thank you to our amazing engineers here. And that's it from Coast Laboratory in Plymouth. Thank you. Bye.